Hey guys, welcome back. We're going to take a look at the Chapter 16 study guide. Here we go. Okay, so just as we've done before, what I'm going to do is, as I fill these out, I will pause to give you an opportunity to answer yourself, and then I will complete the answer. So let's get started. Here's section 16.1, and we have a word bank here: collision theory, activation energy, activated complex, reaction rate, transition state, and moles per liter seconds. According to the blank, atoms, ions, and molecules must collide in order to react. Right, that's collision theory, of course. Atoms, ions, and molecules must collide. Number 2, once formed, the blank is a temporary, unstable arrangement of atoms that may then form products or may break apart to reform the reactants. Sure, it's the activated complex. That's right. That is the temporary, unstable arrangement of atoms. Number 3, this physical arrangement is known as the transition state. Transition state is the correct answer there. Every chemical reaction requires energy, and the minimum amount of energy that reacting particles must have to form the activated complex is the activation energy. That's right. In a chemical reaction, the blank is the change in concentration of a reactant or product per unit time. Sure, the reaction rate is the correct response there. The reaction rate may be expressed using the units of, well, it's the last one, isn't it? So yeah, it has to be moles per liter second. So there we go. First section done. Let's move on. Use the energy diagram for the rearrangement reaction of methyl isonitrile to acetonitrile to answer the following questions. What kind of reaction is represented by this diagram? Is it endothermic or exothermic? Yes, that's right. It's exothermic. You see how the reactants have a higher energy than the products do. Because of that, that means there is a decrease in energy. Energy has been released, and thus it's exothermic. Number 8, what is the chemical structure identified at the top of the curve on the diagram? What do we call that? Yeah, we call that the activated complex. That is that transitionary state structure that can either go back toward reactants or forward to the products. Number 9, what does the symbol E sub A represent? Good. That's the activation energy. That's the energy required to achieve that activated complex state. What does the symbol delta E represent? Delta E represents the net energy. Now, in this case, it represents the net energy released from this exothermic reaction. If you had a delta energy that was up, in other words, the reactants are lower in energy than the products are, that would be an increase in energy, and thus we'd have an endothermic situation. All right, page 1 done. Way to go. Moving on to page 2, we have matching. For each item in column A, write the letter of the matching item in column B. Number 11, this expresses the average rate of loss of a reactant. Well, what they mean here is that we require a negative number for a change in the reactant, don't we? Because reactants are lost in the reaction and products are gained. That's why in our formula we put a negative symbol in front of the change in reactant over time. Since the reactant change is going to be negative, the negative of a negative makes that rate positive. Number 12, expressed as change in quantity over change in time. Sure, that's the average reaction rate. That's exactly how we phrase that. And the last one expresses the average rate of a formation of a product. Of course, that's B, and again, we say that because we're gaining in quantity of products, that's a positive change. And so in our equation, we don't put a negative in front of that. We just leave it positive. And remember, folks, remember, rate is always positive. Rate is never negative. Okay, so we have this figure here describing a reaction taking place, and this is actually the one that I drew on the board in our first video of this chapter. I don't know. This one doesn't do it for me. I think the one on the board was a whole lot better, but hey, that's okay. We'll make do with what we have. So we have here an incorrect orientation that results in a rebound and no reaction. And here we have a correct orientation but insufficient energy, and thus we have a rebound with no reaction. This one is where we have the correct orientation, and then we form the activated complex, which then forms the products. All right, number 14. What molecules collided in collisions A, B, and C? Well, you'd have to look in the book for this or recall what I did on the board in the first video. But this is carbon monoxide and this is nitrogen dioxide. Just so you know, that's not something I would expect for you to remember. I would either give you the equation or give you the reaction and you solve it from there. What do the arrows represent? The arrows simply represent the direction in which these are traveling and also the amount of energy of those moving molecules. It just helps us to know, for example, that these are coming together to collide and these two are rebounding. They're moving away from each other. Which collisions formed products? And what were the products? The answer, of course, is letter B. Letter B is the one in which we have the correct orientation, the correct amount of energy, and we form the products CO2 and NO. So right here, carbon dioxide and nitric oxide. Another name for nitrogen monoxide. Explain why the other collisions did not form products. Okay, collision A, we said, had an improper orientation. If I move back up here, you can see you've got the oxygen meeting up with the oxygen. That's the improper orientation. For collision C, we said that there was proper orientation, but not enough energy. And so that's why those two did not form products. Which collisions formed an activated complex? Identify the activated complex. Of course, letter B was the one. Collision B was the one where we had the activated complex formed. And so we would call this is oxygen, carbon, oxygen, nitrogen, oxygen. So Okono, I guess. Oxygen, carbon, oxygen, nitrogen, oxygen. And there you go. Page 2 down. All right, for this page, we begin section 2. We have the factors affecting reaction rates. We talked about things like reactivity, concentration, surface area, temperature, and even catalysts. So number 1, if it's true, we say it's true. If it's false, we correct the italicized word. Decreasing the concentration of reactants increases the collision frequency between reacting particles. No, that's not right, is it? It's increasing the concentration that allows us to have more particles, thus increasing the collision frequency. Number 2, a heterogeneous catalyst exists in a different physical state than the reaction it catalyzes. This is true. All this means is if I have, for example, a solid catalyst that is activating a liquid system, a liquid reaction, then that would be a heterogeneous catalyst. It exists in a different physical state than the reaction that it is catalyzing. So a homogeneous catalyst in that sense would be if I had a liquid catalyst added to a liquid reaction. You get it? Okay. Number 3, increasing the concentration of a substance increases the kinetic energy of the particles that make up the substance. No, of course, the answer there is temperature. Temperature is what is in line with kinetic energy. Number 4, Catalysts increase the rates of chemical reactions by raising the activation energy of the reactions. No, of course, the answer is actually lowering the activation energy. Catalysts lower the activation energy and thus make it easier for that chemical reaction to take place. Number 5, increasing the surface area of the reactant increases the rate of the reaction. Sure, of course that's true. We saw that in our second video. Number 6, raising the temperature of a reaction increases the rate of the reaction by increasing the energy of the collisions between reacting particles. Yes, of course. We raise the kinetic energy, and that raises the energy of the collisions between the particles. Bottom of the page, a chemist heated a sample of steel wool in a burner flame exposed to oxygen in the air. He also heated a sample of steel wool in a container of nearly 100% oxygen. The steel wool sample in the container reacted faster than the other sample. Explain why. Of course, it's because there's more oxygen in that container. Since there's more oxygen, and that's one of the reactants, we've increased the concentration of the reactant, which increases the rate of reaction. Would the chemist have observed the same results if he used a block of steel instead of steel wool? Explain your answer. No, of course not. That block of steel would have less surface area, and in doing so, it would decrease the reaction rate. Number 9, how would the reaction have differed? How would it be different if the steel wool was not heated? If we don't heat the steel wool, then the reaction rate is lower, since temperature and the reaction rate are directly related. So since the temperature is lower, the reaction rate would decrease. Look at that. We are churning through this. Man, look at us go. All right. 4th page, Section 3, Reaction Rate Laws. We use each of these terms below to complete these statements. And here we have equation 1 that represents a generic reaction for us. And equation 2, we can see two ways of expressing the rate. The rate can be expressed in terms of the negative of the change in reactant over time, or notice it can also be expressed in a rate law. Remember, these two are on the same team, aren't they? This is the rate, and this is the rate. So equation 1 describes a chemical reaction, a generic, in this case, chemical reaction. Equation 2 expresses the mathematical relationship between the rate of a chemical reaction and the concentrations of the reactants. This is known as the rate law. How we have the concentrations of the elements and the rate of the chemical reaction. So rate is equal to K times the concentration of A to the nth power, which we would have to find again experimentally, multiplied by the concentration of B to the nth power. The variable K in equation 2 is the specific rate constant. It's the numerical value that relates the reaction rate and the concentrations at a given temperature. So as long as you keep that temperature constant, that K value will remain the same. The variables M and N are the blank. These define how the rate is affected by the concentrations of the reactants. These are reaction orders, and they're the ones that help us to understand how that rate is changed based on the concentration. The square brackets represent, concentration. Square brackets represent concentration for us. And the variable T represents time. Good, that's correct. All right, let's move on to the next section. The next section is about this particular rate law right here. Number 7, what is the reaction order with respect to A? Since A has an exponent of 1, that means that A is first order. So, if we made a change to A, we would see that same type of change in the reaction rate. For example, if we doubled the rate of A, we would see a doubling of the rate of reaction also. What's the reaction order with respect to B? Right, since B has an exponent of 2, that means that B is second order. In other words, whatever we do to B, we would see the squaring of that in the result for our rate of reaction. For example, if we increased the concentration by a factor of 3, we would see a change in the rate of reaction by a factor of 9, the square of 3. What is the overall reaction order for the rate law? The overall reaction order is the sum of the exponents. So 1 and 2 gives us third order. Number 10, doubling the concentration of A will cause the rate to double. What would happen if you doubled the concentration of B? Sure, the rate would quadruple. Of course, because the square of 2 is 4. So, since you double B, the result would be that the rate increases by a factor of 4. Here's a very simple rate law. A reaction rate can be expressed as the rate is equal to K times the concentration of A squared. What is the reaction order for this reaction? That's right. It is simply a second order reaction. That's the only exponent we have, so that's all we use. Okay, page 5. Instantaneous reaction rates and reaction mechanisms. Circle the letter of the choice that best completes the statement. Well, let me get my circle out here. All right, I'm ready to go. Blank is determined by finding the slope of the straight line tangent to the curve of a plot of the change in concentration of a reactant versus time. We did this in our 4th video. That would be, of course, instantaneous rate. Number 2, a blank consists of 2 or more elementary steps. The correct response is A, a complex reaction. A blank is a substance produced in an elementary step and consumed in another elementary step. The answer is B, intermediate. Number 4. A blank is the complete sequence of elementary reactions that make up a complex reaction. I just said it a few seconds ago, didn't I? Reaction mechanism. That is our sequence of steps. Number 5. The blank is the slowest of the elementary steps in a complex reaction. That's right, the rate determining step. Just like that sibling that makes you all late for church or to the restaurant. Every time, right? Am I right? Number 6. The blank can be used to determine the instantaneous rate for a chemical reaction. This one's D. The rate law can be used to determine the instantaneous rate. Lastly, number 7, an element or compound that reacts in one step of a complex reaction and reforms in another step of the complex reaction is a catalyst, B. This is something we see in a complex reaction, that when we use a catalyst, it may be altered in one step, but then reforms in a subsequent step so that the net result is the catalyst remains unchanged. Pretty cool, huh? Last page. Can you believe that? Wow. Time flies when you're having fun. Okay. Very short true-false section here. If it's true, we write true. If it's false, we change the italicized word or phrase to make it true. Number 8. To determine the instantaneous rate, you must know the specific rate constant, the concentrations of the reactants, and the reaction orders for the reaction. That's true. That's exactly right. When we're using the rate law, those are exactly the things we need to determine the instantaneous rate. Number 9, a reaction rate that's defined as K times the concentration of A times the concentration of B, and that has a specific rate constant of 1 times 10 to the first liters per mole second. That's another way of saying 1 over molar second. And A has a concentration of 0.1 molar and B has a concentration of 0.1 molar, the instantaneous rate would be 0.01 moles per liter second. Not quite. They're off by 1 decimal point, aren't they? It actually has a value of 0.1 moles per liter second. Last section, we have a complex reaction here, and we're going to be asked questions about the mechanism. Number 10, how many elementary steps make up this complex reaction? Sure, the answer is 3. Very plainly, we can see here's 1 step, a 2nd step, and a 3rd step. By the way, does this set of steps look familiar to you? Maybe it's just me. Number 11, what is the rate determining step for this reaction? Why the slow step, of course. The slow step is the rate determining step. It's the one that requires the most activation energy to proceed. Number 12, what are N2O2 and N2O in this reaction? Since N2O2 and N2O are produced in one reaction and then used up in another, those are both, of course, intermediates. Is there a catalyst involved in the reaction? Explain your answer. No, not in this case. There is no catalyst because we don't have any situation where a molecule reacted in one step and was then reformed in another subsequent step. So no catalyst involved in this reaction. What can you conclude about the activation energy for the rate determining step? Of course, the rate determining step has the highest activation energy. Number 15, if you wanted to increase the rate of the overall reaction, what would you do? Well, simply put, we would find a way to speed up that rate determining step. Maybe it involves increasing the temperature, or maybe increasing a concentration, or something along those lines. Nonetheless, we would speed up the rate determining step. Hey, look at that. All done. Man, look at all that work you did. Nice work. Good job. And if you have any questions, please don't hesitate to give me an email. Until next time, God bless.